Hello participants. In last two videos, we have discussed cylindrical coordinates and spherical coordinates. I hope you have found these videos very helpful. Now we will start with fundamentals of electrostatics. I will focus mainly on Gauss's law. Outline of my talk will be basic concepts, some solved examples, and then jam problems. Now, why I am starting with basic concepts, though the theme of the entire course is problem solving techniques. The only reason behind this is basic concepts, if they are very clear, then one can solve any problem. Generally, in our syllabi, except few institutions, very less stress is given on how to solve the problems. That is, how do we go from known to unknown. We are giving more stress only on the known things, and unknown things we just don't try it out. They are not very difficult, they are easy. Problem is we don't know how to apply the basic concepts to problem solving. So I will definitely revise some of the very fundamental concepts because I am not knowing uh, what is being done to you and what is not done to you, because there is a diverse crowd. There are students from 11, 12 standard to post graduation. Some teachers are there. So please bear with me if there is a lot of repetition for you for some of the participants. So let us start with charge configuration. Now, basically, what is a charge? Charge is something which creates an imbalance in the environment. Like I have a uh, object, a ball like thing in my hand. I can hold it because it is uncharged. But if by some means, if I create or if I make it a charged body, then I cannot hold it in my hand because it will start creating a field. Always remember, charge is deficiency of electron or addition of electrons. If it is a deficiency of electron, we call it as a positively charged body, and if it is addition of electrons, we call it as uh, negatively charged body. Now, every time it cannot be a ball or it cannot be uh, something like a line or something. So, there are various configurations of charges. Now, if I have a point charge like here Q1, Q2, Q3, and if this is an assembly, then we call this as a discrete charge, and this charge configuration is called as discrete charges. If I have something like a line charge, means it's a charge line like charge, then I called it as a finite line charge because the things will change the moment this charge becomes infinite. What is the example of this? Supposing you are working with some kind of a CRT, then from anode to cathode, there is a emission of electrons. It will create a line like thing which can be called as a line charge. Now, there is a small element of this line charge which I am denoting as DL. Remember this, we are going to need this quite often. It's a small part of this line charge. Then I have a surface charge. Again, this I am talking about finite surface charge, which is looking like a surface. Now, the best example of surface charge is parallel plate capacitor. There is a small element dA, remember this. Then I have a finite volume charge. Here it is rho. This charge density, here it is called as lambda, here it is called as sigma, and here it is called as rho. Charge density, everybody understands the difference between charges, charge and charge density. The small element of this is called as dV. Now these figures I have picked up from this website, physics.libertex.org, and I thank them for this. So once we understand that there are different varieties of charges: point charge, line charge, surface charge, and volume charge, the field they will create will be also different and will totally depend upon the charge density. So you must be familiar with electric field expressions for various charge configuration. Now remember one thing. In electrostatic study, main aim is always to estimate the electric field E. Now it is a vector quantity for various types of charge distributions such as point charge, line charge, surface charge and volume charge. Now as these derivations are available in any standard textbook, I am not going for any kind of a derivation because we are going to learn how I can use these formulae to solve some problems. So electric field because of point charge is 1 upon 4 pi epsilon 0 I going from 1 to n qi upon r squared r cap, where this is a unit charge. Now I means, like in the earlier example we had seen there were three charges. So if three charges are there, this will be 3. Then next is a continuous charge distribution, which is a line charge. So lambda dl upon r squared into r cap, where lambda is the charge density and dl is that small length element which I was referring to. Then next is a surface charge. This 1 upon 4 pi epsilon 0, I am not going to repeat again or say it again. Maybe sometimes I will say this as a electric constant and just keep it aside. Then it will be sigma dA upon r squared r cap. Then comes the volume charge. It is again integration over volume, rho dV upon r squared r cap. Now you will find this is little different, but these three are absolutely same. For line, you have lambda dl. For surface, you have sigma dl, sigma dA, and for volume, you have rho dV. Now always remember one thing: we measure the electric field at some point and not at the source. I'll just go back to the earlier slide. This is a source of electric field. This is a charged body and this is creating a electric field. I will calculate it somewhere here at this point. Then I'll get something, some value as electric field. Now same value I will not get it here because the direction is different. So the electric field will be changing at this point, at this point, at this point, and at this point. So remember that this is a source charge, and the point where I am going to look at the charge is called as a test charge. So, as I told in my last slide, that the main aim of electrostatic study is to estimate or to calculate the electric field. There are two ways. One is direct application of Gauss's law. I am yet to tell you what is Gauss's law. Or another way is integrating a known charge density over line, surface, or volume. Now, Gauss's law allows us to find electric field without needing to integrate. That is the advantage of Gauss law. Gauss law is less laborious. We don't have to do many integrations. We can quickly calculate the electric field, but there are certain restrictions also. Thus, in the present work or present video, we will see how Gauss's law can be used to solve problems in electrostatics. Now, there is one you should understand that in this presentation, all vectors are denoted by bold case because I found it quite laborious to put that part. Now, prelude. Now, this concept I have taken from Illinois Institute of Technology website. This is not a concept developed by me. I have picked it up and I thank them for that. Now, just consider a circular ring which is charged, and this is a charge Q on it. Now, we want to find out the electric field at a point P here across this at this charge. Now always remember, as I told in a few minutes ago, electric field is estimated at a point under consideration. Now this has, I don't know, shifted. This is x-axis and this is y-axis. I'm sorry for this. This is my charge P. This x is basically for x-axis. Now we can see from symmetry that electric field in y direction cancels out, because what happens, this is and this entire figure is shifted, this should be extending here. So this is going here and this is coming here. So if I draw x-axis and y-axis, it's changing. But look at this, it's cancelling. I'm sorry. And look at this. This is a purple thing and this is a green thing. So this black thing is symmetric. So the electric field at this region and this region will be cancelled. So there is no contribution in y-axis. But look at this. Now what happens here? To find the electric field in x direction, we can integrate it around the whole circle. Now what we find is that since electric field is proportional to the inverse square of a distance, that is our Gauss's law, or we all know that as I go away from the source, the electric field will go on decreasing with square of the distance. It is smaller, closer on the charge on. So here this is smaller and here it is larger at this point. So it is smaller, closer charge on the blue part of the circle and cancels out with the larger but more distant green part of the circle. The electric field therefore at point P will be 0. Now since this kind of a donut is bunch of rings added together, we get some same result for any donut shape. So this is where this symmetry and this cancelling out is basically the prelude of Gauss's law. Now we need certain definitions to be very, very clear and certain concepts to be very, very clear before we really proceed to Gauss's law. First, we will discuss the electric field, or I'm sorry, electric flux. Electric flux is the rate of flow of the electric field through a given area. Electric flux is proportional to the number of electric field lines going through a virtual surface. Now, this is my field lines, and I have imagined one kind of a circular surface. And see, I'm going to discuss certain cases, and these are extremely, extremely important. So, pay attention. If my field, this flux or imaginary virtual surface, which I'm considering, there are only three lines passing through this, and there are 1, 2, 3, 4, 5, 6. So flux is proportional to the density of the flow. So for this the flux is less and for this the flux is more. Now what I am doing is I am just tilting this. So in the same electric field I am tilting this particular virtual surface, then the field lines are changing, so flux will be changing. So flux varies how boundary faces the direction of flow. It is, imagine a water flow, and in that water flow, if water is flowing like this, you have something here, that is what is called as flux. If you get confused, imagine a water flow and just keep some ring or something and see how water flows through that ring and imagine all these cases, or you can do it practically and see how the flux changes. Then flux is also proportional to the area within the boundary. Now, if my imaginary virtual surface is small, the flux will be smaller. If my imaginary surface is big, flux will be big. So now understand this, the electric field is basically perceived, it is the perceived as the flux. So I can't see electric field. I also can't see electric flux. But what I can do is I can very easily calculate those. I don't know. The concept may be very, very difficult. But understand one thing, calculation is very easy. So if I want to calculate electric field, one way to understand what is the electric flux. And this electric flux will be very, very, very crucial as we are going to use Gauss's law. So again, I will speak little bit more on this flux. Little mathematics will be involved. If the electric field is uniform, electric flux passing through a surface of vector area A is. Now I will spend some time on what is this A vector. Phi E is given as E dot A. Both of them, they are vectors. So it will be EA cos theta.